Hey guys, it's Booth Dog again. Here we are at the start of our second week of this new experience for us all. We certainly live in interesting times. Um, I'm grateful to be experiencing this with so many great people like yourselves. Um, just please, I'm going to keep saying this, but especially as this continues longer and longer, just reach out. I'm here if you need anything. Many of us are, okay? Um, Now, to lighten the mood a little, I know many of you have been asking about a house tour, so I thought, why not? So let's go ahead and get started before we bring Mr. Boothman on to give you your lesson for the day, okay? Here we go. All right, good morning. We're back again. We still have about a week to spend on section 8.3. I'm glad to hear that most of you seem to be grasping this concept pretty well. It can be tricky to see these rotations in 3 dimensions, especially as we go on throughout this week. So please keep up the practice, keep asking me questions. You guys are being fantastic. Thank you. Brief announcement. So your exit ticket for today is just going to be, much like last week, submitting a question from today's lesson. I promise tomorrow you will have a bit of a different exit ticket I'll be putting in as a completion grade. I'll talk more about that by the end of this lesson, okay? So let's jump into where we left off. We derived this formula for the volume of one of these solids of revolution. Okay, it's called solid of revolution since we're taking a 2D shape and rotating it in 3 dimensions, okay? So the volume is just the integral from a to b of pi and then big R squared minus little r squared dx, where big R and little r are functions of x, okay? So these are the radii of our shape. So for example, if we have this shape, here's A, here's B, and we're revolving this about the x-axis, okay, then it's going to come up out of the board, back into the board, right here, through the other side, and then back up. Okay, so a cross section is going to look like a washer, where this part is this area all the way around, and then this big part right here in the middle is this gap. Okay, so our little r is the distance from the x-axis up to our first function. Okay, that's this distance right here, from the x-axis up to the first function. Our big R is from the x-axis all the way to the second function. Okay, so that's big R, this distance right here. And I know that's hard to see, I just used the same color. But hopefully you understand what I'm saying. So we have R, big R, little r. We have the area of the big circle minus that area of that smaller circle gap in the middle. We subtract those. That's the area of our cross section. We integrate that. Now, please note, it's a great question I'm getting from some of you. In this case, a cross section had the shape of a washer. What if our shape looked more like this? And we're revolving this around the x-axis. Is that cross section a washer? No. See, there's no gap. So typically, when our function goes all the way up to our axis of revolution, that's what we would call the x-axis in this case, or later today we'll talk about the y-axis, then we end up with a solid circle as we're revolving around that line. Okay, so we're not always using washer method. If it's just a solid circle, then we have volume is the integral from a to b of pi r squared, where r is a function of x. It would just be the function value in this case. So it really depends. We do have 2 different cases. Sometimes it's a washer, sometimes it's just a circle. The basic concept is the same, where we're integrating the area of a cross section over an interval. But it really just depends on what we're rotating around and what our function is. Okay, so some great questions, great questions. Hopefully you're starting to see the difference between these 2. Now let's go back to the washer method specifically, and I suppose even a solid circle. So we talked about using washer method when we're revolving around the x-axis. Okay. Now we can also talk about washer method revolving about the y-axis. Now in this case, our formula is the same. Suppose we have this shape right here, but we're revolving it this way. So the shape is coming up out of the board, hits the board right there, back into the board on the other side, and then comes back up here. So it's creating this three-dimensional shape still. In this case, it's kind of hard to integrate this way. Again, it's a three-dimensional shape. Exactly how are we going to take into account that weird gap in the middle? So when we revolve around the y-axis, it tends to be easier to look at a cross-section here. So our cross-section here is still a washer. Only this time, since we're looking at it from a different perspective, we're not going to integrate this with respect to x. We are going to integrate this with respect to y. So instead of going from a to b, where a and b are the x values of our interval, we're going to go from c to d. So right here is c, and up here is d. Right here is d. And we want the area of a cross-section. It's still going to be this pi big R squared minus little r squared dy. Okay, where in this case, our radii are functions of y. And it's still the same basic idea. Little r is the first function, so the function closest to our axis of revolution. Big R is the function furthest from our axis of revolution. And I promise we are building toward a more general rule for finding those radii in a couple of days, probably tomorrow actually. But for now, I really want us thinking conceptually. Okay, so that big radius is going to be the function that's furthest away from our axis of revolution, whether we're talking about the x or the y-axis. Okay. So it's the exact same formula. It's basically the same setup. We just need to recognize that when we're revolving about the y-axis, or as we'll generalize tomorrow, any vertical line, then we should integrate with respect to y. We're looking at this from a different perspective. Okay, so we are using y values for our limits of integration, and we're using functions of y instead of functions of x. So really, for the rest of today, I want you to focus on practicing. I will do one problem revolving around the x-axis, and then one problem revolving about the y-axis, and then I will ask you to continue practicing yourself. Let's do number 11 together on the third page of our mastery sheet here. So we're told that we have y equals x squared, nice parabola, y equals 0, which is the x-axis, and the line x equals 2. Find the volume of the solid generated by revolving the region bounded by the lines and curves about the x-axis. So let's fill this in right here. So this is the region that's bounded by those three functions. And we're revolving this about the x-axis. So it's coming up out of the board, hits the board right here, revolves on the other side, and then comes back up. And so it's a nice three-dimensional shape. So remember how I said earlier, we're not always using washer method. So let's look at a cross-section. Okay, what is that shape? Is it a solid circle, or is it a washer? Well, since our region goes all the way up to our axis of revolution, there's no gap. Okay, so we are actually dealing with a cross-section that's just a solid circle, which means that our volume is going to be from, well, we're starting at 0 and going to x equals 2, so 0 to 2, of a of x dx. We're integrating with respect to x. We're revolving around the x-axis. And the area of this cross-section, it's a circle, so pi r squared, where r is this distance right here, which ends up just being this function value, in this case, x squared. So pi, x squared is our radius, and we're squaring our radius in the area formula. And this ends up being the integral that will give us our volume. Now this is something you can hopefully quite easily integrate by hand. So many of you have been asking this question, great question. Up until now, I've really just been asking you to practice setting up these volume integrals. That's really the hardest part of them, and it's a weird thing to get used to. You can be asked to actually evaluate and find the volume. Okay, so in this case, please evaluate this integral. We take an antiderivative, evaluate it from 0 to 2, and we end up with 32 pi over 5 cubic units. Okay, so we do find the actual volume at times, and you shouldn't have needed a calculator for this. This was, the antiderivative is 1/5 x to the 5th pi from 0 to 2. That's not terribly difficult for you. Okay, so from this point on, it usually specifies, I think, for basically this entire page, it is asking you to evaluate and find the volume. Okay. So 12, 13, and 14 work pretty much the same way. Always check, do we have a solid circle or do we have a washer? I would like you to work on those yourself. We will talk about numbers 21 and 22 tomorrow. You do not yet quite have the skills to do that. That's what tomorrow's lesson will cover. But jumping down to numbers 23 and 24, I'll do one of them, and then I'll ask you to do the other. Let's do number 23 together. So, kind of the same setup. Okay. Find the volume of the solid generated by revolving the region about the y-axis this time. So let's start by setting this up. The region enclosed by x equals the square root of 5 y squared. Anytime we have a variable squared like this, y equals x squared, x equals y squared, it's a parabola, okay? But when we have x equals y squared, it is a sideways parabola. And that square root of 5 is just going to be a transformation of it. So general shape is a parabola, sideways. We want the region enclosed by this, x equals 0, which is right here. And the lines y equals -1, and y equals 1. So this area in here, and we're revolving this area around the y-axis. So this whole area, it's kind of weird, coming up out of the board, hits the board right here, and it goes back in, and then continues revolving about till it hits the other side. So again, this if I could draw this three-dimensionally, it would be a three-dimensional, almost a perfect hourglass shape, actually. And we want the volume. Now, since we rotated this with respect to the y-axis, we revolved it about the y-axis, then it is going to end up being easier to think of taking cross-sections horizontally instead of vertical cross-sections. And taking any cross-section here, do we end up with a washer or a solid circle? It goes all the way up to our axis of revolution, so it is a solid circle. Okay? So our volume is the integral from, remember we're dealing with y values now since we're integrating with respect to y, so -1 to +1. And we want the area of a cross-section in terms of y. So if we think about a circle here, pi r squared, but r is going to be the distance from the y-axis over to this function. And what function is that? It is the square root of 5 y squared squared. So this is what we're plugging in to our integral. Again, this is something that is simple enough for you to evaluate by hand. If we do that, we should get an answer of 2 pi. Okay. So there we go. So all that's due by midnight tonight is any question you may have about today's lesson. Now, tomorrow, instead of the same exit ticket, I am going to ask you to submit pictures of your completed third page of this mastery sheet. So we just did 2 of these problems together. So that's all done. By the end of the day tomorrow, I will want numbers 12, 13, 14, 21, 22, and 24 completed. 21 and 22 you won't be able to do until tomorrow's lesson, so that's fine. If I were you, I would get all the others done today. That way tomorrow you only have those 2 problems to do. You are going to submit pictures of that work to a Google form. I'll post tomorrow, and then I'm going to put that in as a problem of the day completion grade. Okay, so practice. Okay, it's just kind of weird to start thinking about, but once you start to get it, hopefully it starts to sink in and make some sense. So join our Google Meet if you have questions. Reach out to me with any other questions or concerns. Otherwise, you just have a simple exit ticket for today, looking ahead to a little more work that's due tomorrow. So please stay on top of things. Let me know if you need anything. Thank you. All right, well, I hope today's lesson was entertaining for you, was interesting at least. Please do your assignment. You know, it's kind of obvious when the view counts on my YouTube videos are lower than the number of people turning in exit tickets. So, you know, watch the video before you just submit a question for the day. You know, we will be doing unit exams in the coming weeks, so you are responsible for this. These are real grades. This is your grade. You are getting credit. So keep on top of everything, okay? Reach out if you need anything. Otherwise, take care. Wash your hands. Be safe. Like and subscribe.